Welcome! In this session, we'll dive into LeetCode problem number 856, score of parentheses. This problem challenges us to calculate the score of a balanced parentheses string based on specific rules. We'll explore the problem, break it down, and discuss an efficient solution. Let's get started. In this problem, we are working with a balanced parentheses string S, and our task is to calculate its score based on three specific rules. First, any single pair of parentheses, represented as, has a score of 1. Second, if we have two balanced parentheses strings placed next to each other, their score is the sum of their individual scores. Finally, if a balanced string is wrapped in an additional pair of parentheses, its score is doubled. For example, the string A has a score of 2 times the score of A. A balanced string means that every opening parenthesis has a corresponding closing parenthesis. The input is a string containing only the characters, and the output is an integer representing the calculated score. To make this clearer, let's look at some examples. For the first example, the input string is, which is a single pair of parentheses. According to Rule 1, any single pair of parentheses has a score of 1. Therefore, the output here is 1. In the second example, the input string is. This can be thought of as A, where A is a smaller balanced string. From Rule 3, the score of A is 2 times the score of A. Since the score of is 1, the score of becomes 2 times 1, which equals 2. Hence, the output for this example is 2. Now, consider the input string. This consists of two separate sets of parentheses, which can be interpreted as A plus B, where A is, and B is also. Using Rule 2, the score of the string is the sum of the scores of A and B. Since both A and B have a score of 1, the total score becomes 1 plus 1, which is 2. For the fourth example, the input string is. Let's break this down further. The string can be understood as A, where A is the substring, plus. First, calculate the score of A. The substring has a score of 1 by Rule 1, and the substring has a score of 2 by Rule 3, as we calculated earlier. Adding these together gives A a score of 1 plus 2, which equals 3. Now, applying Rule 3 to the outer parentheses, the score of A becomes 2 times the score of A. So, we multiply 2 by 3, resulting in a total score of 6. This gives us the final output for this example, which is 6. To ensure your solution works for all scenarios, consider these edge cases. First, a single pair of parentheses, such as, tests the base case. Second, nested parentheses like, or, evaluate Rule 3, where the score is doubled for the outer layer. Third, multiple independent groups, like, test Rule 2, where scores are summed. Finally, deeply nested structures, such as, test the handling of depth and proper multiplication at various levels. Keeping these cases in mind will help validate the correctness and robustness of your solution. To solve problem number 856, score of parentheses, we need to compute the score of a balanced parentheses string based on the problem's specific rules. Let's start by considering different approaches. One approach is brute force using recursion. The intuition here is that the nested structure of parentheses naturally lends itself to recursion. By breaking the string into smaller segments, we can compute the score of each portion individually. For example, we identify the innermost pairs, assign them a score of 1, and then calculate scores for larger balanced segments by summing the scores of their parts. However, implementing this approach involves repeatedly slicing the string to isolate segments, which is computationally expensive. This makes the time complexity O(n squared), and it also risks exceeding recursion depth limits for deeply nested strings. While recursion provides a clear and intuitive way to model the problem, its inefficiency makes it less suitable for larger inputs. Another approach is to use a stack-based simulation. This method is ideal for handling nested structures, as stacks allow us to track the depth and compute scores incrementally. Here's how it works. We begin by pushing a 0 onto the stack to represent the score at the outermost level. For every opening parenthesis, we push another 0 onto the stack, indicating a new depth. For every closing parenthesis, we pop the top of the stack, which represents the score of the innermost segment. If this score is non-zero, we double it, as per the rules for nested parentheses. We then add this value to the next item on the stack, representing the score at the outer level. At the end of the process, the top value on the stack contains the total score. This approach processes each character exactly once, giving it a time complexity of O(n), and the space complexity is O(n), as it depends on the maximum nesting depth. The stack-based simulation is both efficient and intuitive, making it a strong candidate for solving this problem. An optimized alternative is the depth tracking approach, which eliminates the need for a stack by using a single variable to track the current depth. Here's how it works: we maintain a depth variable, incrementing it for each, and decrementing it for each. When we encounter a closing parenthesis, we check whether the previous character was an opening parenthesis. If it was, we calculate the score for this innermost pair as 2 raised to the power of the current depth and add it to the total score. This is because the depth determines the contribution of each pair to the overall score. This approach runs in O(n) time, as we still process each character once, but it only uses O(1) space, since we don't need to store intermediate states in a stack. While this method is highly memory efficient, it's slightly less intuitive to implement and debug compared to the stack-based approach, especially for those unfamiliar with the specific scoring logic. When comparing these approaches, the brute force method provides a clear recursive structure but is impractical for large inputs due to its O(n²) time complexity and recursion limitations. The stack-based simulation, on the other hand, offers an efficient solution with O(n) time and O(n) space complexity. It's straightforward to implement and easy to debug, making it a reliable choice. The depth tracking approach is the most optimized in terms of space, requiring only O(1) auxiliary memory, but it sacrifices some clarity and can be harder to implement correctly. Ultimately, the stack-based approach strikes the best balance between simplicity, efficiency, and ease of understanding. This makes it the preferred strategy for solving the problem effectively while maintaining clarity in the implementation process. In this problem, we are tasked with calculating the score of a balanced parentheses string based on 3 key rules. First, a single pair of parentheses has a score of 1. Second, if a pair of parentheses wraps around another balanced string, such as A, its score is twice the score of the inner content. Lastly, the score of 2 independent balanced strings, like A plus B, is simply the sum of their individual scores. To solve this, we'll explore a brute force approach that leverages recursion. The idea is to break the string into smaller balanced substrings, calculate their scores independently, and combine them based on the problem's rules. To begin, the base case is straightforward. If the input string is, we directly return a score of 1 because that's defined by the problem. Now we move to the recursive case. If the input string is not, we need to analyze its structure to determine how to compute the score. The first step is to check whether the string can be divided into 2 independent balanced substrings. To do this, we use a balance counter. As we iterate through the string, we increment the counter for every, and decrement it for every. When the balance counter returns to 0, it indicates that we've found a valid split point between 2 independent balanced parts. At this point, we recursively calculate the scores for the left and right substrings and return their sum. Additionally, if the entire input string is wrapped in a single pair of parentheses, like A, this is an encapsulation case. Here, we calculate the score of the inner substring and multiply it by 2, reflecting the nested structure. These cases are implemented recursively to handle any valid input string. When implementing this algorithm, it's important to consider edge cases to ensure robustness. For example, the input will never be empty since it's guaranteed to be a balanced parentheses string. For a single pair, we return 1 as defined. For nested pairs, such as, we must ensure the recursion correctly calculates the inner scores step by step, resulting in a score of 4. For multiple independent substrings, like, the algorithm must sum their scores properly, giving 1 plus 1 is equal to 2. At its core, this recursive solution relies on a divide-and-conquer approach. By dividing the string into smaller balanced components, solving each independently, and combining the results, we can compute the score efficiently. The balance counter plays a critical role here, as it ensures we identify valid split points for independent substrings. Additionally, encapsulation cases, like A, are handled separately to ensure nested structures are scored accurately by doubling the inner result. While the recursive approach effectively solves the problem, we should also consider its efficiency. The algorithm involves splitting the string and processing each part recursively, which can lead to a worst-case time complexity of O(n) squared, due to repeated slicing operations. The main data structures involved are the input string itself and the recursion stack, which manages intermediate computations for nested substrings. To clarify how this works, let's walk through an example. Consider the input. First, since the base case doesn't apply, we look for independent substrings. Using the balance counter, we find the first valid split occurs at index 3, dividing the string into, and. Next, we handle each substring recursively. For the first, it's recognized as an encapsulation case with an inner substring of, which has a score of 1. Doubling this gives a score of 2. The same logic applies to the second, also resulting in a score of 2. Finally, we combine the scores of the two independent substrings. Adding 2 and 2 gives a final score of 4. While this brute force recursive approach works, there are opportunities for optimization. For instance, we can avoid repeated slicing by passing indices instead of substrings during recursion. Additionally, we can explore alternative solutions, such as using a stack-based approach, which can reduce the time complexity to linear. This would involve iterating through the string while maintaining a stack to calculate scores dynamically, making the algorithm more efficient for larger inputs. By understanding both the recursive approach and its optimizations, we can appreciate how to analyze and improve solutions to complex string-based problems like this one. The provided Python implementation calculates the score of a balanced parentheses string using a stack. The main idea is to process the string character by character and use the stack to keep track of scores for nested and independent groups of parentheses. First, a stack is initialized as an empty list. Each character in the input string S is then iterated over. If the character is an opening parenthesis, we push a 0 onto the stack. This 0 acts as a placeholder to mark the start of a group. If the character is a closing parenthesis, we pop the top of the stack. If the popped value is 0, indicating a simple pair, we push 1 onto the stack, which represents its score. If the popped value is not 0, it means we are closing a nested group, A. In this case, we calculate the total score of the nested group by summing all scores on the stack until reaching a 0, the corresponding opening parenthesis. Once the total score is calculated, it is doubled, as per the rule for A, and pushed back onto the stack. Finally, after processing all characters, the stack contains scores of all independent groups of parentheses. Summing these values gives the total score of the string. This approach ensures that we correctly handle both nested and independent groups of parentheses. The complexity is O(n), since each character is processed once, and stack operations are efficient. This solution is concise and handles all edge cases, such as deeply nested or completely independent parentheses groups. Here, we start by importing the necessary packages and defining our solution class with the method score of parentheses. This method takes a string S as input, representing a sequence of balanced parentheses. To calculate the score, we use a stack to keep track of intermediate values. As we iterate through the characters of the input string, we check whether the current character is an opening or closing parenthesis. If it's an opening parenthesis, we push a placeholder value, 0, onto the stack. This helps us mark the start of a new group. If it's a closing parenthesis, we handle two cases. First, if the top of the stack is 0, it means we have an empty pair, and we push a score of 1 onto the stack. Otherwise, we calculate the score of nested groups by summing up the values on the stack until we encounter the placeholder 0. Once the inner scores are combined, we apply the rule for A by multiplying the inner score by 2 and pushing it back onto the stack. After processing all characters, we calculate the total score by summing up the values remaining in the stack. Since the stack may contain scores from independent groups, we pop each value and add it to total score. Finally, we return the total score as the result. This approach ensures that we correctly calculate the score for both simple and nested parentheses groups using a stack-based method. To begin solving the problem, let's look at the simplest example where the input string is just a pair of parentheses. We start with an empty stack. As we process the first character, which is an open parenthesis, we push a placeholder value of 0 onto the stack to represent it. Now, the stack contains one element, 0. Next, we encounter the closing parenthesis. At this point, we pop the top value from the stack, which is 0. Since the popped value is 0, this indicates a simple pair of parentheses, so we push the score of 1 back onto the stack. Finally, to compute the total score, we sum all elements in the stack. Since the stack contains only one value, 1, the final output is 1. This demonstrates how the algorithm handles the simplest case of balanced parentheses. Now, we examine a slightly more complex example with the input string. Again, we start with an empty stack. The first character is an open parenthesis, so we push 0 onto the stack, resulting in 0. Then, we encounter another, so we push another 0 onto the stack, making it 0, 0. Next, we process the closing parenthesis. We pop the top value, which is 0, indicating a simple pair of parentheses, and push the score of 1 back onto the stack. Now, the stack becomes 0, 1. After that, we encounter another closing parenthesis. This time, we pop the top value, which is 1, and continue popping to find the enclosing open parenthesis, represented by 0. The popped score of 1 is the nested score, so we calculate the score for the enclosing pair, A, by multiplying the sum of the nested scores by 2. In this case, 1 multiplied by 2 equals 2, so we push 2 back onto the stack. The stack now becomes 2. Finally, we sum all elements in the stack to get the total score. Since the stack contains just one value, 2, the final output is 2. This illustrates how the algorithm handles nested parentheses. Next, let's analyze a more complex example with the input string. Starting with an empty stack, we process the first character, which is. Pushing 0 onto the stack results in 0. Then we encounter another, and another 0 is pushed, making the stack 0, 0. When we process the next character, we pop the top value, which is 0, and push 1 onto the stack to represent the score of this simple pair, resulting in 0, 1. We then encounter another open parenthesis, so we push 0 onto the stack. The stack becomes 0, 1, 0. Next, we process another, and push another 0, resulting in 0, 1, 0, 0. Then we process a closing parenthesis. Popping the top value, which is 0, indicates a simple pair, so we push 1 onto the stack. The stack now looks like 0, 1, 0, 1. After that, we process another closing parenthesis. This time, we pop the top value, which is 1, and continue popping to find the enclosing open parenthesis, represented by 0. Summing the nested scores gives 1, and multiplying by 2 results in a score of 2, 4, A. We push 2 back onto the stack, which now becomes 0, 1, 2. Finally, we process the last closing parenthesis. We pop the top value, which is 2, and sum all nested scores within the enclosing parentheses. The sum is 3, and multiplying this by 2 gives us 6, representing the score for the entire structure. We push 6 onto the stack, and the stack is now 6. In the final step, we sum all elements in the stack, which results in 6. This is the final output, demonstrating how the algorithm computes scores for more complex, nested structures. The time complexity of our solution is O, n, where n represents the length of the input string s. This efficiency comes from the fact that the algorithm processes each character in the string exactly once during a single pass. Let's break it down further. First, the loop iteration itself is O, n, since we traverse the string from start to finish, handling each character one by one. Next, the stack operations are performed in constant time, O, 1, for each operation. This includes pushing a 0 onto the stack for each, and popping, summing, or pushing results when encountering. Finally, the nested score calculation, or scores for groups like A, are popped, summed, and pushed back, is also constant time per nested group. Adding these together, the algorithm's total time complexity is O, n, since each character contributes to a single operation, and all stack operations are efficient. The space complexity of this solution is O, n, and this is primarily due to the use of a stack. In the worst-case scenario, where the input consists of solely nested parentheses, such as, the stack can grow to a maximum size of n/2. This happens because each results in an entry being pushed onto the stack, and the stack size won't start decreasing until all the corresponding are processed. Beyond the stack, the algorithm only uses a few integer variables, such as top and inner underscore score, for intermediate calculations. These variables require constant space, O(1). However, since the stack dominates the memory usage, the overall space complexity of the solution is O(n), which is directly proportional to the input size. Now, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, where there are no nested parentheses, such as each pair of parentheses is processed in constant time, resulting in a linear time complexity of O(n). In the average case, which features a mix of nested and non-nested parentheses, the algorithm still processes each character exactly once and uses constant time stack operations. This means the average case also maintains a time complexity of O(n). Finally, even in the worst case, where the input has deeply nested parentheses the algorithm processes every character in a single pass and performs efficient stack operations. This ensures that the worst-case time complexity remains O(n). Compare this to a brute force or naive approach, which might recursively parse substrings and could result in O(n²) time complexity due to redundant operations. Our algorithm avoids such inefficiencies. Comparing the current solution to a brute force approach, we see clear advantages. The current solution achieves an O(n) time complexity, which is significantly better than the O(n² complexity of naive methods that involve recursive parsing or substring operations. While both approaches have a space complexity of O(n), due to either stack usage or recursion depth, our solution is more streamlined and efficient in practice. To mathematically prove the O(n) time complexity, observe that each character in the string is processed exactly once, and every stack operation, whether it's a push, pop, or sum, is O(1). The total operations are therefore directly proportional to the length of the string. Similarly, the O(n) space complexity arises because the stack size grows linearly with the depth of nested parentheses, reaching O(n) in the worst case for deeply nested inputs. Ultimately, this algorithm is both time and space optimal for solving the problem. Here, we're looking at some common mistakes to avoid when solving the score of parentheses problem. A key issue is misinterpreting the base case where some might fail to recognize that its score is explicitly 1. This is critical because serves as the foundation for all calculations, and missing this can throw off your entire solution. Another common pitfall is confusing nested parentheses with concatenated ones. For example, in a nested structure like AB, the score is doubled, whereas concatenated structures like A plus B simply add scores. Mixing these concepts results in incorrect outputs. It's also important not to overlook edge cases such as deeply nested structures or flat concatenations. These test how well your solution handles various patterns. Finally, improper stack management can create issues, especially if you're not pushing or popping at the correct times. This can lead to mismatched scores or even runtime errors, so careful handling of the stack is crucial in stack-based approaches. Inefficient recursive calls are another common mistake to watch for, particularly when recursion is used without memoization. This can lead to redundant calculations and significantly increase time complexity, especially for larger inputs. On the interview side, this problem is a great opportunity to demonstrate your ability to balance stack-based, recursive, or iterative strategies. Interviewers often look for how well you can convert recursive logic into an iterative solution, which is a valuable skill. This problem also highlights the importance of recognizing and processing nested structures, a critical skill for solving tree or graph-related problems. Additionally, interviewers may ask you to optimize your solution, such as by discussing the time and space trade-offs of recursion versus stack-based methods. Be prepared to explain how your approach distinguishes between operations like doubling scores for nesting and adding scores for concatenation. Clearly articulating your thought process is key. This problem also ties into several related problems on LeetCode that you might find helpful. For example, LeetCode 20, valid parentheses, focuses on basic stack usage for validating parentheses. LeetCode 32, longest valid parentheses, deals with finding the longest valid substring, which requires handling nested and valid parentheses. Then there's LeetCode 921, minimum add to make parentheses valid, which emphasizes adding parentheses to balance a string. And finally, LeetCode 1021, remove outermost parentheses, challenges you to identify and remove outermost parentheses, often using a stack or a counter. Exploring these related problems can deepen your understanding of how to work with parentheses and stack-based techniques. Now let's discuss alternative approaches and their trade-offs. The recursive approach can be elegant and straightforward, but it tends to introduce high space complexity due to the stack frames, making it less efficient for large inputs and less optimized. A stack-based approach, on the other hand, is highly efficient in both time and space, operating at O(n). However, it demands careful management of stack operations to avoid errors. Another option is the iterative approach using counters instead of explicit stacks. While this can slightly reduce space usage, it's often harder to implement and debug, especially for beginners. Lastly, the divide and conquer method involves parsing substrings, which can be conceptually intuitive. However, it often leads to redundant calculations, pushing its time complexity to O(n)² in some cases. Each approach has its strengths and weaknesses, so understanding their trade-offs is essential for choosing the best solution for a given context. Great job! We've explored the score of parentheses problem, discussed an efficient solution, and highlighted key takeaways. Keep practicing and building your problem-solving skills. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!